my name is Amanda. I am the satellite meteorologist at NOAA's Aviation Weather Center in Kansas City, Missouri. And so for the last part of the presentation, I will be providing a perspective of the GOESR Proving Ground from the Aviation Weather Center. So first I wanted to start out by just giving a brief update on GOESR. So this is the current schedule of our current constellation as well as our upcoming future constellation. We have currently in orbit, we have GOES 13 and 15. 13 is our GOES East satellite, 15 is GOES West. We have our on-orbit spare of GOES 14, which we take out of storage for if one of our other satellites has an issue, which we've done a couple of times, and we have also used it to test out some super rapid scan. So some 1-minute imagery sectors throughout various periods this past summer and spring. We have also some more of those periods scheduled for next year to get a first glimpse at the temporal resolution that will be provided with GOESR. You can see further down there we have the newest series of GOES satellites, which is R, S, T, and U. GOESR is scheduled currently to be launched within an October 2016 window. After that, it'll go through 6 months of post-launch testing, followed by another extended 6-month post-launch testing period, during which time products will start to be disseminated, and it will become officially operational roughly a year after launch. So why do we need GOESR? GOESR is our next advanced series of satellites, and it'll provide us significant improvements in the detection and observations of meteorological phenomena and improve our forecasting process. Not only will it have enhanced visual and IR imagery, but it is also unique in that it has a geostationary lightning mapper. I'll talk more specifically about these instruments a little bit later. But both of these will have the potential to improve our hurricane track and intensity forecasts, thunderstorm and tornado warning lead times, aviation flight route planning, marine forecasting, climate, and a lot of other things. Additionally, GOESR also has 4 space weather instruments. These instruments are also pretty unique and fairly new, and you don't often think of space, at least I don't, think of space weather when thinking of weather forecasting, but it really can cause significant impact, especially such things as magnetic storms. And these space weather instruments will definitely be able to help with that aspect. So to start out with, this is the GOESR system architecture for the United States. We have our main data acquisition station at Wallops Island, Virginia, to our satellite operations facility on the East Coast in Sweetland, Maryland, and we also have a backup facility in West Virginia. And from there, data will be able to be disseminated to our other users, including our international partners. This will be via the GOESR rebroadcast or via PDA, which is NESDIS's, or our Satellite Operations Facility's newest product dissemination system, which will be going active within the next year or so, I believe. And as you can see there, GOESR will be, in its post-launch checkout period, will be positioned at 89.5 degrees west, which is a central position over the United States. Additionally, GOESR also has the ability to do search and rescue satellite-aided tracking. It also has the ATRIT MWIN information network, which I believe we also have with our current constellation. We also have the data collection system, which relays data transmissions to quite a few different environmental data platforms across the hemisphere. And then, as I mentioned, we also have the GOESR rebroadcast, which takes information from each of the GOESR series instruments, processes them on the ground, and then bounces them back through our GOESR satellite to our international partners. I do see a question in the chat box, and I will actually address the position of GOESR in just a few slides here. As far as data distribution, this is a figure that shows a little bit of how it will go, with your fastest data dissemination at the top. Moving down towards the bottom of the graphic is where your slowest receipt of data will be. The fastest is obviously going to come from the direct broadcast station itself. If you have, I know that some international partners are planning and other users are planning to have a direct readout ground station or antennas on site, which the Aviation Weather Center is one of those. If you do not have one of those, again, the data will be transmitted back to the satellite and out to our international users through the rebroadcast, and then it will also be available via the PDA, the Product Distribution and Access System. This system will be sending out not only just the general cloud and moisture imagery, but it'll also be sending out derived products, and that will go to National Weather Service users in the United States, as well as our other operational user community throughout the hemisphere. We will also be sending this data to archives like CLASS, which is a very large climate archive, who also provides data to users. This latency tends to be the slowest, however, because it has to go through a lot of channels before it gets there. So there is a lot of ways that we can get GOESR data out there to our users. So launch and post-launch testing. Launch and the extended 6-month validation period, we will be testing level 2+ products. So basically any derived products, including atmospheric motion vectors and other derived products. Once it becomes operational, it will be given the name GOES-16, and 1 year after, and roughly we will hope that it'll be about a year after launch. This graphic on the right here shows GOESR at our checkout location, which is central. Where it ends up after launch when it becomes operational is still to be determined, and it's highly dependent on the health of our current constellation. So if we have an issue with either our GOESR East or our GOES West satellite, we'll have to adjust. And again, it's the position of where GOESR ends up is highly dependent on that, so it's yet to be determined. This graphic here shows an image of the spacecraft and the instrumentation. Again, we have the Advanced Baseline Imager, and for those of you who have seen AHI imagery from the Himawari satellite, you know that it's very, very similar to that. We also have the Geostationary Lightning Mapper, which I'll talk a little bit about in the upcoming slides, and then we have a series of 4 space instruments. This is a graphic or an image of the assembled GOESR spacecraft at the Lockheed Martin facility in Colorado. You can see the PGL instrument there on the top and the ABI instrument on the bottom of the payload, and you can also see its solar wing there. Currently, it's undergoing some final testing, and we hope for the launch in October of 2016. So now I wanted to talk a little bit more specifically about the instrumentation and the capabilities of GOESR, specifically the Advanced Baseline Imager and also the Geostationary Lightning Mapper. So the Advanced Baseline Imager, again, is very similar to the AHI on Himawari if you have begun to receive that data where you are located, or if you have seen any of that. We will have 5 times faster coverage or temporal resolution. We will have 4 times improved spatial resolution, and we will have 3 times more spectral bands than our current GOES constellation. So this is just a list of the 16 ABI bands. This is bands 1 through 6 here. When they were picking out these bands, they had to consider this pretty carefully because unlike our current GOES constellation, GOESR will not have a sounder. It was planned for at first, but it will not have that at launch. And so they wanted to pick some of these bands to mimic what the GOESR sounder does now so that we do not lose those capabilities. And some of those bands, such as levels of water vapor and the IR bands, were included for that reason. This is a visual idea of what the 16 bands of the ABI will look like. I did want to make a note that it isn't exactly the same as AHI. There are a couple of subtle differences, but again, it is very close. This is proxy ABI simulations of Hurricane Katrina, looking at all 16 bands. as compared to the 5 bands that we currently have. So it is a huge improvement in the number of spectral bands that we have. And now moving on to temporal resolution. And for those of you who have already downloaded the animations before this presentation, now would be a good time to pull those out, since I know some connections are slow and even mine is a little bit slow. Temporal resolution, we will have the ability to see 1-minute imagery. I think the animation's on the next slide. I'll have to wait for it to load just here for a minute, but this image here, this animation here is from Hurricane Igor. This is off the Pacific coast, and it looks like I'm getting an error. But if you can see the animation, it's a comparison of 1-minute imagery versus the current 30-minute temporal resolution that's available over the oceans. And this is off the Pacific Ocean, and so you can see just how much extra detail and features that you can pick out with the 1-minute temporal resolution versus the 30-minute latency. Okay, I guess my screen is the only one that was having the error, but all right. So spatial resolution, we again are going to have twice the spatial resolution that we have now. This is an example this is actually using NOAA 15, the AVHR imager, to show what it would look like. So this would be a sample of current GOES resolution. This is some convection over northern Alabama, so this is the southwest United States. And this would be at our the new GOESR resolution, so it's very much improved. And then again, will be great benefit to pick out features, particularly cloud features and weather features. We also, because of the type of the type of imager that the ABI is, it can scan multiple places at once. So we have the ability to have far more complex scan modes. Now we have about a series of 6 that have been proposed. However, the main scan modes are going to be 3 and 4, last I heard. Scan mode 3 is considered a flex mode. And so what that is you will get a full disk every 15 minutes. You will get a CONUS scan every 5. And you will get 2 locations with a 1-minute mesoscale sector. And you can see those 3 sectors here on this slide. Scan mode 4 is a continuous full disk, and that provides a full disk scan every 5 minutes. So again, this is as compared to our current GOES constellation, where we have our routine scan operations that provides about a 15-minute, occasionally 30-minute image over the CONUS. South American scans, I believe, twice an hour, small areas of those, and full disk only every 3 hours. So it's a big improvement as far as scan modes go as well. This here shows a listing of all the available baseline products that will be available as soon as GOESR becomes operational. So this includes the ABI imagery as well as derived products like cloud optical depth, some of the lightning detection, drive motion winds, and many, many others. All right, so moving on to the geostationary lightning mapper. This instrument will be able to detect total lightning activity across the Western Hemisphere. This is in cloud, cloud to cloud, and cloud to ground, which is very beneficial, as right now most of our lightning detection networks that we have available can only detect cloud to ground, which, as you may or may not know, is only about 15% of all lightning activity. So being able to detect that extra lightning will be particularly beneficial to severe weather and also aviation interests, as well as others. Additionally, the GLM will provide a lot more coverage over oceans, as well as land. And the graphic here on the bottom left, you can see the footprint of the GLM, whether it ends up in an east or west position. You'll note that it is not all the way to the poles. It's not a complete full disk, because once you get further up into the limbs of the satellite perspective, you start to lose your detection efficiency. So again, the footprint is a little bit smaller than a full disk. And the data, I believe, is 8 kilometers. And then just briefly, this is a list of the space weather instruments. A number of these are meant to better detect solar flares as well as magnetic storms that can cause some serious disruptions to communications. Being in the aviation industry, the aviation community here, I know what kind of effect that can have on aviation communications. So having these instruments will be very important. And additionally, there's the SUBI instrument, which is designed to further study the sun. So as you can see by the improved spatial resolution, temporal resolution, and the increased amount of spectral bands and derived products that are going to be available, we have a proverbial fire hose of new data that is coming in. So how do we prepare for that? Well, the US came up with the GOESR Proving Ground concept. This is a group of Weather Service offices and centers, as well as research entities around the United States who collaborate in the research to operations effort. So the research entities will take GOESR data, in this case GOESR proxy data, using the current GOES constellation, GOES East and GOES West, to produce GOESR-like products. They also will use polar satellites for some of this as well. They will test these, they will send them to Weather Service offices and centers across the United States to determine whether or not those products would be useful and try to integrate them into operations so that we're prepared on day one. Now, this was a challenge at first because if you just send a product to an end user or a forecaster, it's going to be very difficult for them in their busy operations to take a look at this product. And so in 2005, the GOESR Program Office came up with a vision of 2 to 3 satellite champions, or liaisons, who would be integrated side by side with forecasters from Weather Service offices and national centers across the US, with the goal that these liaisons would prepare and train forecasters for data that would be available on GOESR, who would ease the transition of the research to operations process. In other words, be the two in that research to operations and operations to research, and also become satellite subject matter experts at those centers and within the National Weather Service. And in 2008, the first satellite liaison was hired for the Storm Prediction Center. And you can see on the right here a couple images of the satellite liaisons now. And also in this slide, we currently now have 8 satellite liaisons, not only in our National Weather Service offices via the Operations Proving Ground, as well as Alaska and Pacific region, but also in our training division, and also in many of our national centers. As I mentioned, I am the satellite liaison at the Aviation Weather Center. And Bernie is asking to point out which one I am. Let me put on my laser pointer. This is me right here. And myself and my counterparts, we have interacted with over 140 forecasters and analysts within our centers, and have also assisted half of all of the National Weather Service forecast officers with evaluating and providing feedback on GOESR demonstration products and participating in GOESR user readiness. So we have been able to reach out to a lot of our weather services to get prepared for GOESR so that we're ready on day one. And now I just wanted to, for the last part of this presentation, provide you a perspective of a satellite liaison from the GOESR Proving Ground at the Aviation Weather Center. I wanted to show you a little bit about what we do and how we integrate products into our operations. So to start with, I wanted to describe a little bit about the responsibilities of the Aviation Weather Center. I like to throw this graphic out here. This is flight routes all across the globe, and the Aviation Weather Center is unique in that we are one of 2 world area forecast centers, the other being in Exeter in England. And as a world area forecast center, we are responsible for, in some manner, forecasting for every single one of these flight routes. So it's a big responsibility. We also have to consider airspace, because in aviation, it doesn't really matter just what's going on over your head with the weather. It matters what's going on wherever your airplanes are, which could be anywhere from the surface to the top of Class A airspace, which is about 60,000 feet. This graphic on the right is U.S. airspace, so I'm sure it differs in your varying countries, but the idea is the same. It's a very large vertical domain that we have to deal with in the aviation industry. We also have to think about and consider all aspects of flight. I would say the vast majority of AWC products are issued for in-flight hazards, such as turbulence, icing, ceilings and visibility, freezing levels, wind shear, and that sort of hazard. However, in the past 3 years, we have also been working very, very closely with our Federal Aviation Administration. We have several forecasters who work directly with their flow managers on forecasting for hazards that are in and around our major hubs and en route airspace, which is typically New York, Atlanta, and Chicago. So because of this large responsibility, we rely very heavily on satellite data, and not only our domestic satellites, but also international and polar. And so it's important that our operations are robust and that we are prepared as soon as a new satellite comes into orbit, into operations. And so the goal of the GOESR Proving Ground at the AWC is twofold. The first is ground readiness, and the second is getting used to the new capabilities, the new products. On the ground readiness end of things, we are, again, as I mentioned, one of those sites where we actually have a direct readout ground station. So we have 3 antennas that can pull data in directly from the satellites. We are expecting 3 more of these antennas to be installed within the next 3 months or so. This red box here on the bottom portion, the bottom right graphic, is where those will be installed. This is the Aviation Weather Center building where I work. And we are, again, expecting those antennas to be installed within the next 3 months. We are working with Harris Corporation in Florida to do that. And to keep our operations robust, we will also be utilizing the PDA system as a backup. So if we have an issue with our antennas, we will have code that automatically switches and pulls data from PDA instead. And yes, Bernie, to answer your question, it's 3 antennas, 1 for east, west, and spare, once all of the GOESR constellation are launched and in orbit. So the next slide, the AWC is unique in that we're an international forecasting area. So we have a lot of, and again, if you have previously downloaded these animations, I would pull up the one listed here on the screen right now. So instead of having our forecasters have to sift through a Meteosat image to a Meteosat 7 image to a Himawari image to the GOES series satellites, we patch them all together. This is an animation of a North Polar stereographic where we patch together polar and also geostationary satellites to look down at the poles. We have more of these. We also have South Polar stereographics, and again, this is for our international forecasters, so they can get a complete view of their domain. And one of our goals is to integrate GOESR data into these mosaics. There we go. We also do mosaicing domestically. So we have, this is image here is an example of a vis and IR mosaic. So during the day, we'll use a visible image here on the right, and at night, we will do an 11 minus 39 micron fog difference so that we have one consistent image from the day to the night. Again, so it reduces the number of images that our forecasters have to flip through. And again, the goal will be to integrate GOESR into these mosaics. And this final one is an example of a global mosaic that we use. So this uses all international and domestic satellites as well as polars to give us a global view of our forecast area. And then for these last few slides, I wanted to talk about some of the derived GOESR products that we have been testing over the past 3 years via the GOESR Proving Ground. The first of which is the Fog and Low Stratus. The Fog and Low Stratus is a fused product. It uses visible and IR data to provide a probability of IFR conditions. For those of you who are not familiar with instrument flight rule conditions, that is equates to, I believe, a quarter mile and 1,000-foot ceilings. Which for some larger commercial aircraft they can still land in. However, for some other ones who don't have as updated of instrumentation, they are unable to land in. In this particular case, it's a little bit difficult to see, but there was some IFR conditions, and if I had an animation of this, you would see those conditions progressing off of Lake Michigan over Chicago O'Hare Airport. Chicago O'Hare is one of the busiest, if not the busiest, airports in the United States. Our meteorologists who work with our Federal Aviation Administration saw that these low ceilings were approaching because of this product, and they talked to the FAA center near there, who was able to talk to the airport and the airlines and tell them to prepare for these conditions, meaning that the aircraft who would be coming in and out would add extra fuel in case they needed to hold. This was about 5 to 7 a.m. local time in Chicago, and there was about 60 flights that were coming in and out. Had these flights had to divert, it would have cost about roughly $10,000 per flight. But because the IFR conditions were seen coming on shore and they added extra fuel, there were no diverts needed. So they ended up saving roughly about $600,000 in extra fuel. And keep in mind that this is goes east and goes west proxy. So goes west is going to be even better. So you can see the potential of GOESR data already via this product. Skip that one. Another big one for aviation is icing. Our forecasters are required to have a top, put a top and a base of the icing layer in their products. And GOESR will have the potential to derive a base and a top of that icing level, which is really important if you have an aircraft who gets caught in the icing layer and needs to either descend, ascend, or divert around this layer. Having those levels is extremely important. So this example here is of icing bases. This is the icing tops. And again, it's very important to have the tops and the bases of icing layers. This is a fairly new product, and we are continuing to evaluate it this year to try and improve the capabilities of it. And outlined in the green boxes is some icing airmets that were issued in this particular case. Simulated GOESR imagery. This is model simulated imagery, so it's basically a future look at what in this case, water vapor satellite image would look like. And this was originally designed to provide a look at the potential capabilities of the additional spectral bands of GOESR. However, our forecasters also like to use this as a forecast tool. In this case, they were looking at some turbulence. They added some turbulence parameters on top. The pink and the green there is a Richardson number, and also some divergence tendency. And that blue, this blue box here, is a turbulence segment. So using this information, combined with information they already had, they were better identifying where that turbulence segment would need to be issued or narrowed down. Cloud top altitudes. For the vast majority of AWC products, we are required to forecast a base and also a height. One of the things that we have been throwing back and forth with the researchers is to try and improve the product is the color table. We can tweak the color table so that in this particular image here, the colors are identifying cloud tops between the surface and 18,000 feet. 18,000 feet is a threshold where our smaller general aviation aircraft can't fly above. It's a Federal Aviation Administration regulation. But we can also flip that around and look at just the cloud top heights at 18,000 feet and above if you're looking for convection, for example. And you can also change it. You can see this image on the bottom right here to look at cloud tops of just 30,000 feet and above. 30,000 is a very important level for convection. The rule of thumb within our FAA is that once it gets above 25 to 30,000 feet, aircraft must start to divert around that convection instead of going above it. And so knowing exactly where those higher tops are really helps our traffic flow managers as far as figuring out where they need to divert aircraft and when they need to start doing that. So again, cloud top altitudes are very important for our forecasters, and we've been able to try and we've been able to put together these color bars as we collaborated with the researcher who produces this product. In the future, this upcoming year, we anticipate getting a convective cloud top altitudes and also a cloud ceiling height product. And that has also come from this research to operations effort with the researchers. The near Cassidy model, this is one of those products that takes advantage of our current sounder bands and will be available via GOESR because of the additional spectral bands. Basically, this is an instability parameter. So it's using the water vapor levels to look for your instability would be looking for a lot of lower level moisture over upper level drying, and that is in the purples, blues, and light blues that you see. Whereas your instability would be where you have drying all through the layer, and that is in the oranges and the yellows that you see in this image. In this particular case, we had a deep trough digging into the United States, and you can see those stabilities, that stability associated with that trough, and you can also see some instability associated with it. This is really important and helpful as far as forecasting convection mode and also porosity. It's a 0 to 9 hour forecast, and it's very important for aviation forecasters to know when convection will forecast, if it will be scattered or a line or a large area like an MCS, and what time that convection will mature and decay and be out of the area where aircraft need to fly through or land. And so this is one of those products that is very helpful for that, because if there's ongoing convection, they can identify if it's moving into an area of instability or stability, and if they're waiting for convection to form, they can get an idea of the environment and where it might, what type of convection they might expect. And it's been very beneficial to be used with other tools as well, current model tools and observations. Dust is another hazard that is very significant, can cause significant issues to aviation. This image was simulated from VIIRS and MODIS imagery because this capability currently isn't available on our GOES constellation. Dust can cause as many ceiling and visibility issues as snow and fog can. However, you can very rarely see it on satellite or radar. This is a VIIRS MODIS true color image shown here. This is over the southwest US, where this was a year ago, April. They often have dust storms in this part of the country this time of year because of strong troughs that come through and bring very strong jets with them. This is a true color or a fancy visible image from a polar satellite over the southwest US. And just looking at it, you can't really tell where the dust is. But the dust enhancement uses visible and IR properties, as well as the characteristics of dust particles to highlight only the dust. And if we look at it, you can see it in the pink color there, how well that dust is picked out. And this is very helpful for our forecasters because we have to issue blowing dust sigmets in our operations, and being able to actually see where the dust is, as opposed to current satellite and radar, helps them identify how big that sigmet needs to be and how long that it needs to be issued for. And this is another one of those products that is currently being used in our operations in an experimental sense. Volcanic ash is another huge one. This is an example actually from Himawari from the new AHI data. The top left image here is an RGB, so that's it's basically looking at a number of the different spectral bands and differences to highlight the volcanic ash. In this case, this is off the Kamchatka Peninsula of Russia, and there was a volcano that erupted and sent out some ash into the Aviation Weather Center's airspace, and Alaska Aviation Weather Unit's airspace. GOESR will have the capability to provide an ash cloud height, an ash loading, so how thick that ash cloud is, and also an ash or dust effective radius, so how big the particles of dust are in that ash cloud, which is very, very helpful to know because ash causes serious issues to aircraft engines. And GOESR will have the ability to vastly improve our detection of volcanic ash. So those are just a handful of products that we have looked at. There are a few more that I didn't put on here, but again, it's working with the research entities to make these products better, and then specifically in the case of the Aviation Weather Center to integrate them into our operations and figure out and prepare so that we are ready day one for what GOESR is going to have available. My counterparts at the National Hurricane Center, at the Ocean Prediction Center, at the Storm Prediction Center, and also at the Weather Service offices, they all have different concerns, and they have all been working with the researchers to integrate products for their specific concerns. And in this way, we have been able to become very prepared for the launch of GOESR, and we're very much looking forward to its launch next October. So just to summarize, just some general thoughts for you. If you guys are in the footprint of GOESR and you haven't thought about what you're going to do to prepare, we would encourage you to do so. There's improved temporal and spatial resolution. There's an increased number of spectral bands and derived products. And this is beneficial not only for the United States, but also for our international partners. We have ample information about GOESR out there for general users at goesr.gov, and also the training page at goesr.gov. Additionally, there's information that you can find at the WMO Saturn portal. I was poking through that before my presentation, and there's a lot of good information there as well. And if you have an interest in promoting GOESR in your office, please speak up. If I can't answer your questions, I will happily try to point you to someone who can. And that is all I have. I'm happy to field any questions.